Hi all, welcome you all to another video of Rapid Recall series. Today we are going to discuss about surface tension. So first equation of surface tension is F equals TL, where F is force due to surface tension, T is surface tension, or that is called coefficient of surface tension, and L is contact in length, and that is actually the contact in length which is open to atmosphere. And this is how the equation is used. Say we have a coin floats on a liquid like this. So let's assume surface tension of the liquid as T, right? If there is T, now the conducting length can be written as 2 phi r, the circumference of the coin, if the radius is r, right? So therefore, if I need to determine the surface tension here, apply F equals TL. F equals T times L contact in length. Contact in length here is 2 phi r. So surface tension force here is 2 phi RT. Surface tension force here is 2 phi RT. And since the liquid is lifted up, this force acts on the liquid in upward direction. So on the liquid that is upwards, then on the object that is downwards. Surface tension changes with temperature, with changing temperature. So this is the variation of surface tension with temperature. So when temperature increases, surface tension decreases in a rapid manner. So it rapidly decreases. The next equation we have to know is pressure difference across a liquid meniscus. Liquid meniscus is any curved shape of a surface of the liquid in a liquid. So that is called a liquid meniscus. Pressure difference across a liquid meniscus can be written as delta V equals 2D over R. And delta V is the pressure difference. And when we consider a liquid meniscus, pressure inside the liquid meniscus is always greater than that outside the meniscus. So therefore, if we expand delta V, it will be P1 minus P2, where R is radius of meniscus. As an example, this is how we can use this equation to write the pressure at a point. So let's write Px. Starting from atmosphere, P naught. Now here, we have to cross this meniscus. Now I am crossing the meniscus from inside to outside, So therefore, from in to out, minus 2D over R. Now we are here. We have to come down the liquid a distance h plus h rho g. Now we add x, so equals Px. So this is how the equation is used. So therefore, if we are jumping into a meniscus, that is plus 2t over r. So if we are jumping out from a meniscus, minus 2t over r. The next thing you have to know is variations of pressure. Now, if pressure difference across a liquid meniscus is known, now we can plot the variations as well. Here, this is atmospheric pressure, constant. And at this point, we are jumping out from the meniscus, minus 2t over r. So this drop is 2t over r. And from here to here, that is constant because same level pressures of a liquid is constant. And again, at this point, increases and atmospheric pressure, and this is plus 2t over r. So likewise, we can plot pressure variations using pressure difference through a liquid meniscus like this as well. Other learnings in hydrostatics should also be used when plotting this. So this is the equation of surface energy in surface tension, that is E equals delta AT, where delta A is the change of area. Change of area is always written as final area minus initial area. Let's see how this equation is used. Let's assume this soap membrane is dragged using a force F, and we are going to determine the work due to surface tension. Apply this equation. E equals delta AT equals final area will be D times L plus X. Final area D times L plus X minus initial area D times L. When we are using surface tension equations for soap, we have to use 2D instead of T because soap membranes, soap films are in contact with the atmosphere from its both sides. So therefore, we are using 2D instead of T into 2T. Simplify this. Dx into 2D. So E equals 2dxt. 2dxt, and this is the work done in this case. Okay, we can determine energy of a soap bubble also using the same equation. Right? If I apply the equation, E equals delta AT equals delta AT. Delta A is final area minus initial area. Final area is area of a sphere. So bubble is a sphere. Sphere, area of a sphere is 4 pi r squared. 4 pi r squared minus initial area is 0 because there was no soap bubble at all initially. There was no soap bubble at all. Times, we have to use 2t instead of t when we are using with soap. Simplify this. 8 pi r squared t, this is called the energy of a soap bubble. Next, if we move on to the equations of capillary rise and capillary depression, capillary rise is H rho g equals 2t over r, where r is radius of meniscus. But if there is an angle of contact, it will be H rho g equals 2t over r cos theta, where capital R is radius of tube and theta is angle of contact. And for capillary depression also, the basic equation without angle of contact is H rho g equals 2t over r, that is same, simple r is radius of meniscus. And if angle of contact is theta, the equation is modified as H rho g equals 2t over r cos 180 minus theta, where capital R equals radius of tube and theta equals angle of contact. So this is everything you have to know in surface tension as theories and as equations. I hope this video helps you to recall it in surface tension. Let's meet in another video. Goodbye.